Hello, we are going to continue uh, discussing organic compounds, cycloalkanes, and their stereochemistry. Last time we talked about structure of a 3-membered ring, 4-membered ring, and 5-membered ring. We'll pay attention to the 6-membered ring today, and we'll try to draw the detailed conformational structure of a cyclohexane and try to understand the relationship with their relationship with an energy. Here's the structure of a cyclohexane. But we know the 6 carbons in the cyclohexane are not in the same plane because they are puckered. The way of puckering is very systematic in cyclohexane structures. If you look at the cyclohexane structures, let's try to look at cyclohexane structure in a more real way. Usually black color is a carbon and blue and red spheres are the hydrogens, right? So you have 12 hydrogens in the cyclohexane, but we can divide the 12 hydrogens into 2 different kinds. One group of hydrogen is perpendicular to the ring axis. Okay, ring axis means we can imagine an axis penetrating the plane of a 6-membered ring. We can also consider the plane perpendicular to the ring axis. Okay, and the plane including 6 carbons and perpendicular to the ring axis is called the ring equator. We can classify 12 hydrogens into 2 classes. One class of hydrogens is parallel to ring axis, and the other class of hydrogens, which is the blue, is included in the equator plane. Actually, we have 6 hydrogens in the which are perpendicular to the ring axis. Also, we have 6 hydrogens included in the ring equator, and they are represented like this. Blue hydrogens are included in the ring equator, and 6 red hydrogens are parallel to the ring axis. We call red hydrogens axial hydrogens because they are pointing. Their CH bond is pointing axial axis, parallel to axial axis. Blue hydrogens is called equatorial hydrogens, and this CH bond with the blue hydrogen is called the equatorial bond. This CH bond with the red hydrogen is called the axial bond. Okay, so if you look at 12 hydrogens of the cyclohexane, we can divide the 12 hydrogens into 2 groups. One group is 6 axial hydrogens, and the other group is 6 equatorial hydrogens. Here is the more realistic structure of a cyclohexane ring. We have carbon, hydrogen, and like this. The red one is axial hydrogens. We have axial hydrogens here, but it's in the back. Okay, and axis is pointing to you. Okay, we have 6 equatorial hydrogens around the 6-membered ring. We understand the relative position of axial hydrogens and equatorial hydrogens. They are completely different. Axial hydrogens is pointing north or south of the axis, but the equatorial hydrogens are included in the equatorial plane, right? When we draw six-membered rings, we have to consider the puckering. When we consider the puckering of six-membered ring, each carbon is trying to avoid to minimize the strike hindrance, right? To minimize strike hindrance, also to minimize the angle strain and torsional strain. So the carb, in this case, this carbon is pointing down, pointing up, down, up, down, up, down. So that's the way how six carbons in the cyclohexane rings are puckered. And each carbon has two hydrogens, and there are two hydrogens attached. And two hydrogens can be divided into axial hydrogens and equatorial hydrogens. Let's think about the axial hydrogens. It will be like this. Be careful that axial hydrogens is pointing down in this case because this carbon is pointing down. This carbon is pointing up. Then axial hydrogen will also be pointing up, down, up, down, up. Okay. How about equatorials? This is equatorial CH bond, and this equatorial should be parallel to the first neighboring CC bond and the next CC bond. Okay, it should be parallel to the bond next to the neighboring CC bond. Okay, so this should be parallel to this, and here's the first one. This is second one. This should be parallel to this. Of course, these two should be parallel. When you draw the chair conformation, don't be confused, all right? You have to understand it. Also, these hydrogens should be parallel. We can understand all this parallel, right? Also, when you draw the carbon rings, this should be parallel to the opposite CC bond. This should be parallel to this. This should be parallel to this, right? Now, if we combine equatorial and axial positions, it's like it will be like this. So let's okay. So for example, this is axial. This is axial. This is axial hydrogens. This is axial. This is axial. And this is axial. But this is equatorial. This is equatorial. Equatorial hydrogens. This is also equatorial hydrogens. This is also equatorial hydrogens. So we can this is also equatorial hydrogens. When you draw these equatorial bonds, be careful. This should be parallel to this, okay? So don't draw this bond like this, okay? Don't draw like this, okay? This cannot be, all right? Now, this is a completed structure of cyclohexane conformers. What happens? Wow. All right. Because this is a complete structure of a cyclohexane. So axial, equatorial, axial, equatorial, axial, equatorial. Okay, we can understand it. All right. This should be parallel to this, and this should be parallel this, parallel to the axis. Okay. Important aspect of conformation of the cyclohexane is their dynamics. If you have a chair conformation of the cyclohexane here, we can move this carbon up. Because this is down, you can move this up. Because this is up, we can move this down, right? Then you will have this one goes up, this one goes down, then you will have the other chair conformations. And we call this is flipping of a ring, flipping of the ring, and this is ring flip. This ring flipping occurs frequently in the cyclohexane ring. But even if it undergoes ring flip, one chair conformer will be converted into the other chair conformer. So, for example, let's think about the ring flipping of a monosubstituted cyclohexane. This is bromocyclohexane and the monosubstituted, right? This is a chair conformation of a monosubstituted cyclohexane, and let's consider this is an axial, okay? And this is equatorial, and we can put it down, and you will have this, right? And you can put this up, then you will have the other conformers. Now, if you compare these two conformers, in this case, the BR is axial position, and CH is equatorial position. But if it undergoes ring flipping, the BR in the axial position is changed to the equatorial position, and H in the equatorial position is changed into the axial position. Okay, so the ring flipping changes relative position of substituents. Also, we can consider about the energies. In this case, this Br is larger than hydrogens, right? In this case, the large group is in axial position. In this case, the large group is in equatorial position. Usually the large group prefers to be in an equatorial position due to the energy stability, right? And so in this case, left one is in higher energy than the right one, okay? Because Br is in equatorial position here, but the Br is in the axial position here. So we can draw the energy of axial bromo compound is like this, and the other equatorial bromocyclohexane is here. But if we consider the energy of the intermediate, energy of in the middle, which is the boat conformation, the energy of boat conformation is higher than the energy of chair conformation because of the you have a CH and you have another CH here. They have very highest static strains. Also, there are a lot of torsional strain between CH. So that torsional strains and the static strain causes this boat form in a higher energy. So we can draw the energy diagram like this, right? If there is an energy difference between two conformers, they will determine the population by this equation. That's the energy difference, and that's the equilibrium constant, gas constant, and temperature. If there is no energy difference, delta G0 equals to 0, then in that case, equilibrium constant will be 1. That means the population of two conformers will be 1 to 1. We are going to talk about the 1,3 diaxial interactions. 1,3 diaxial interaction means interaction between diaxial substituent in 1,3 position. For example, here is you have 1 and y is in axial position, and 2 and 3 is you have 3 and h is in axial position. Then we call the interaction between h, axial h, and axial y is 1,3 diaxial interaction, right? The reason we consider 1,3 diaxial interaction is because they are statically hindered, and they gives the static strain. And this static strain between 1,3 axial substituents make the conformer destabilized. For example, here, let's take a look at the CH3 compound, monosubstituted cyclohexane, metal cyclohexane. In this case, CH3 is in actual position. This is a real structure. If you look at the structure, this CH3 is actually very close to these two actual hydrogens. That's why you have a steric strain in one-state diaxial interactions. But if these metal groups is in an equatorial position like this, they are pointing away, and we can consider this hydrogen is relatively far away from this CH3, and we don't have to consider destabilization due to the one-state diaxial interaction. What's the energy of the one-state diaxial interaction? This is a butane compound, and then the source representation of butane. If we look at the Newman projection of butane, this is a staggered form, right? And there is the energy due to these two methyl groups, and we know this is a Gaussian interaction. We know the interaction energy is 3.8 kilojoule. We already learned that in last chapter. Actually, the one-state diaxial interaction between this CH3 and H is also 3.8 kilojoule. It's the same. The reason it's the same is because in this case, this CH3 looks like this CH3, and this CH2, and this C and C bond is like a C and C bond. And this CH is just like a CH in CH3, even though this is CH2, but we can just consider this is just like the same as, approximately same as CH3. If it is the same as CH3, then this is just this CH3 and this CH3 is just like a Gaussian interactions. Because they are like a Gaussian interactions, the interaction should be 3.8 kilojoules, right? So in this case, you have two one-state diaxial interactions when the CH3 is in the actual position. But if CH3 is in equatorial position, then there is no one-state diaxial interactions. So energy difference between these two conformers will be 7.6. Now we can calculate relative population between these two conformers using this equation, all right? You can just calculate it at home. Depending on the size of this substituent, depending on the size of this Y, the energy of one-state diaxial interaction will be different. If you have a very large group like this, wow, the energy of one-state diaxial interaction is very large. But if you have a very small substituent like OH instead of CH3, it's 2.1. We know that if Y is CH3, the one-state diaxial interaction will be 3.8. So depending on what kind of substituent you have, the amount of one-state diaxial interaction energy will be changed, all right? Let's try to consider the energy and conformation of a disociated cyclohexanes. We will consider 1,2-dimethyl cyclohexane. If you draw the structure of 1,2-dimethyl cyclohexane, we can consider two stereoisomers. One is cis and the other one is trans. Cis means two methyl groups are on the same side, and trans means two methyl groups are on the opposite side. So this is a structure of cis, all right? You have two methyl groups are on the same side. If two methyl groups are on the same side, one methyl, because this is 1,2-dimethyl cyclohexane, they are adjacent to each other. If they are on the same side, but they are adjacent, in that case, if one CH3 is in axial, then the other CH3 should be in equatorial, because if you look at here, this is axial and this is up, this is down, so the equatorial should be up. Therefore, two CH3, if this is in the cis 1,2-dimethyl cyclohexane, one methyl group will be in an axial and the other methyl group should be in equatorial position. If it undergoes ring flipping, then the two methyl groups will change their position, and axial becomes equatorial becomes unaxial. Now let's try to think about the energy of this, the first conformer. In this case, let's try to think about interaction between these two, carbon 1 and carbon 2. That is gauge interaction, okay? You think about the Newman projection between 1 and 2 and try to think about what kind of limitation we have between these two CH3 groups. That's gauge conformation. If you look at this carbon 1 and 2, right? So there is one gauge interaction between red CH3 and blue CH3. Also, there are two one-3 diaxial interactions between H and CH3 because blue CH3 is in the actual position. But there is no one-3 diaxial interaction in the red color because the red CH3 is in equatorial position. So therefore, the energy of this system 1,2 diameter cyclohexane will be 1 gauge and 2 1,3 diaxial interactions. And we know 1,3 diaxial interaction between H and CH3 is 3.8. Therefore, the energy of this compound will be 3.8 plus 3.8 multiplied by 2 because you have two 1,3 diaxial interactions. It will give 11.4 kilojoule. Even if it is on the ring flip, situation is the same. One CH3 is axial and the other one is the other CH3 is in equatorial positions. Therefore, the energy will be the same as 11.4. Therefore, we can the population between these two conformers will be 1-to-1 because there is no energy difference between these two conformers. Both of them are in the same energy, 11.4. So the relative population between these two conformers will be 50% and 50% because they are in the same energy. How about trans? If you have a trans 1,2 diameter cyclohexane, you have now let's think about the conformation of trans 1,2 diameter cyclohexane. Trans means two metal groups are pointing away, right? So, for example, here, if they are this metal group is pointing up, this metal group is pointing down, so they are trans, right? But in this case, these two metal groups are in actual position, okay? But it will undergo ring flipping, okay? If it undergo ring flipping, axial will be changed into equatorial, and equatorial will be changed into axial. So therefore, this blue will become equatorial. This red will also become equatorial. And by ring flipping, there are two conformers in trans 1,2 diameter cyclohexane. Let's try to think about the energies. Here, there is no 1,3 diaxial interaction between H and CH3. There is only one gauge interaction. So energy of this compound will be 3.8. However, in this case, you have two 1,3 diaxial interactions due to red CH3, and you have another two 1,3 diaxial interactions due to blue CH3s. Therefore, the energy will be 3.8 multiplied by 4. That gives 15.2 kilojoule per mole. There's a large energy difference between this 3.8 15.2. So the population will be much more favored for the this conformer, which has two CH3 groups in equatorial position. This reflects the principles that larger groups in a cyclohexane, larger substituent in the cyclohexane prefers to be in an equatorial position because they want to avoid energetically unfavorable 1,3 diaxial interactions. For polycyclic compounds, let's try to consider the fused ring of two cyclohexane rings, right? This is cis because both of them are pointing up. In this case, CH is pointing up. The dotted line represents pointing down. Therefore, these two hydrogens are trans. We call, if six cyclohexane rings are fused together, we call decalin. And because both hydrogens are on the same side, these two CC bond should be these two rings should be on the same side also. Therefore, this compound is called cis decalin because two 6-membered rings are on the same side. In this case, these two hydrogens are opposite side, so these two rings should be opposite side. So we call this as trans decalin. Let's try to draw the three-dimensional structure of a cis-decalin and trans-decalins. For a cis-decalin, you have one cyclohexane rings, and these two hydrogens should be on the same side. Because this should be on the same side, one hydrogen should be in an axial position. The other hydrogen should be in a equatorial positions, all right? Because this is axial position, this should be in equatorial position, and this is an equatorial position. So this carbon bond should be axial position, all right? So this is axial position. It should be perpendicular to the equatorial plane. So the structure should be drawn like this, all right? About transdecalin, they are pointing away. So in this case, ring in these two CC bond cannot pointing away because they are in a ring structure. So in order to make a transdecalin structures, two hydrogens should be pointing each other away. So two hydrogens should be like this in both of them are in an axial position, and both of the CC ring, CC bond in the ring should be in an equatorial position. Okay, so this equatorial, and you complete the other rest of the cyclohexane, and it will give a structure like this. Okay. Now we talked about the three-dimensional structure of organic molecules. There is a very nice program called PyMol, which can view, which can allow you to see the three-dimensional structure of molecules, as long as you have data file, right? So PDB website, you visit PDB website and you can get the data file for three-dimensional structure of the molecules, and then once you have the data file, you can easily see the real structure of the molecule in a three-dimensional structure. In order to see it, you need a program, and so we call molecular viewing program. Okay, you visit this site and you can download the PyMol program, and you visit PDB website and get the data file and use this PyMol program, and you can try to see the molecules. You can see the small molecules, but you can also see the large molecules like this, like proteins. There are data files. You can import the data from the PDB website, and then try to see the real structure of the molecules. So if you have if you're interested in, try to download the PyMol program and try to practice it. Okay. Draw two constitutional isomers of cis-1,2 dibromocyclopentane. Okay, here you have to draw constitutional isomers, all right? If we can easily tell the stereoisomers of this compound, the other stereoisomers will be trans 1,2-dibromocyclopentane. But the question asks us the constitutional isomers. Constitutional isomers means you have to break the bond to make the other isomers. So in this case, the constitutional isomers, this is 1,2, so the constitutional isomers will be like a 1,2 dibromo, but 1,3 dibromo will be constitutional isomers. You can move this other carbon here, and this 1, 2, 3, 4, but this is not real 4. The position will be, if you count from the other way, 1, 2, it will be 1, 3, 4. It will be 1, 2, 3. So even if you have a Bl here or Bl or here, they are the same compound. So actually you have the constitutional isomer which has a bromo position in the 3 positions. But you have 2 choices. You can put this bromo up, or you can put this bromo in the down. So actually the constitutional isomers of cis-1,2 dibromo cyclopentane will be cis-1,3 dibromo cyclopentane and trans-1,3 dibromo cyclopentane will be a constitutional isomers of cis-1,2 dibromo cyclopentane. Okay, like this. Okay, we just learned very important thing about the conformation of a six-membered ring. One important thing is that if you look at the carbohydrate like glucose here, you have HOH like this, but you also can consider chair form of glucose, and OH is larger than hydrogen, so OH prefers to be in equatorial position like this. Right here you have H, CH2OH, CH2OH prefers to be in an equatorial position. Okay, so we can apply the concept of a conformational isomer or concept of the conformation to the glucose molecules, and we can easily understand why OH is always in equatorial, not in axial position. If it is in axial position, we have to consider 1,3 diaxial interaction between OH and H. Okay, it makes the molecule unstable, right? And so the molecule always prefers to have OH in an equatorial position in glucose molecules. And this is an example how we can apply the concept of a conformational energy into biomolecules. Okay, that's about it. Okay, we'll meet in chapter 5 next time. Bye.